You know that feeling when an AI generates a whole essay or a piece of code in just a few seconds? It feels like actual magic, but it's not. It's this incredible symphony of software and hardware working together. Today, we're going under the hood. We're heading deep into the engine room of AI to see how the low-level code that talks to the silicon makes these amazing high-speed models possible.
So, here's the plan. First, we'll dig into the single biggest bottleneck that slows down pretty much all large AI models. Then, we'll meet the expert's toolkit, Cutlass, which is designed to just smash that bottleneck. After that, we'll see how Python is putting all this power into the hands of way more developers. We'll check out a real-world breakthrough from DeepSeek. And finally, we'll look ahead and figure out what all this means for the future of AI. So, let's start with the big question. What's the #1 challenge for these giant AI models? Well, it really all boils down to one thing: cost. And I don't just mean the price tag. I'm talking about the cost in time and in raw computational power. Training and running these models is just incredibly expensive, and that's the core problem we're going to unpack today. To tackle that cost, you first have to find out where it's coming from. You have to find the source of the inefficiency. And it turns out, at the very heart of almost every single neural network, there's one operation that's doing most of the heavy lifting and creating most of the cost.
That operation is called GEM. It stands for General Matrix Multiplication, and you can really think of it as the engine of AI. Every single thought an AI has, every word it spits out, is the result of just countless matrix multiplications. It's the most fundamental operation, but it's also the most expensive one. So if we want to make AI cheaper and faster, this is exactly where we need to focus our attention.
Okay, so if GEM is the engine, how do you tune it up for maximum performance? Well, you go straight to the engine builders themselves. And that brings us to Cutlass, which is NVIDIA's super specialized toolkit for squeezing every last drop of performance out of their GPUs. So what exactly is Cutlass? Well, it's not some simple tool you just download and run. It's more like a box of high-performance Lego bricks, but they're made out of C++ code. Performance engineers can use these bricks to build custom solutions, we call them kernels, that are perfectly optimized for their specific AI model, letting them get as close to the bare metal as possible. And Cutlass has really evolved over the years. It started back in 2017 as this incredibly powerful, but also incredibly complex C++ library. Version 3.0 started making things a bit easier, but the real revolution, the real game changer, came with version 4. This is when Python entered the scene, and that changed everything.
At its core, Cutlass is all about giving experts ultimate control. It lets them slice and dice these huge math problems, work with all sorts of different data types, and make sure everything is perfectly optimized for the latest and greatest hardware. It is the ultimate toolkit for wringing every last bit of performance out of a GPU.
But here's the catch. All that expert-level control, it comes with a seriously steep learning curve. You had to be a real C++ wizard. So what about the rest of us? This is where the story gets really interesting, with the rise of something called domain-specific languages, or DSLs for short.
And the impact of this shift is just massive. I mean, don't just take my word for it. Listen to what NVIDIA themselves said in their documentation. They said, DSLs offer a much smoother learning curve, orders of magnitude faster compile times, and native integration. In other words, it's a huge leap forward for actually getting work done.
I mean, the difference is just night and day. The old way meant you had to be a deep C++ expert, and then you'd wait forever for your code to compile. The new way lets you use the Python you already know, it compiles in a flash, and it integrates smoothly. This isn't just a tiny improvement. It's literally opening the door to innovation for a whole new generation of developers.
And a perfect example of this is a project called Tile Language. It's a Python DSL that lets you write just a few lines of simple, clean code. But behind the scenes, it's generating these super optimized CUDA kernels that are just as fast as the ones handcrafted by experts. This is what the fast lane for AI innovation looks like.
All right, so we've seen the problem, that big GEM operation. And we've seen the solution, these incredibly powerful new tools. So now, let's see what happens when we put them to the test on a really tough real-world challenge. Let's talk about the new DeepSeek-V3.2 model.
Let's just start with the headline, because it's a big one. 10x. That's it. By using these new techniques, DeepSeek was able to make processing a huge amount of text, we're talking 128,000 tokens, 10 times cheaper. This isn't just a small step, it's a total game changer.
A 10x improvement is, well, it's huge. So you have to be wondering, how on earth did they do it?
The secret isn't how the model pays attention. They move from a brute force method to something much, much smarter. They call it DeepSeek Sparse Attention, or DSA. Now, the old way, dense attention, made every single word in a document look at every other single word. It works, but it's incredibly slow and inefficient. DSA is way more clever. It intelligently picks out only the most important words to focus on, and that drastically cuts down on the amount of work the GPU has to do.
So here's how it works, broken down into 3 pretty simple steps. First, this thing they call a lightning indexer does a quick scan of the text and gives every word an importance score. Then a selector component just grabs the top 2,048 most important words. And finally, all of that heavy-duty computation, that expensive attention mechanism, is done only on that small, super relevant group of words. It's simple, but it's genius. And this table really says it all. The computational complexity goes from exponential down to linear, which, trust me, is a massive, massive deal. But forget the theory. Look at the bottom line. The cost plummets from over $2 to just 25 cents. That is the real-world power of smart optimization.
So we've gone on quite a journey here, right? From the deepest levels of C++ code all the way up to a breakthrough AI model. But let's zoom out for a second. What does all of this really mean? Why is this shift from super complex tools to much simpler ones so important?
Here's the key takeaway. The one thing to remember, making hard things easy is how you accelerate innovation, period. When you give more people the power and the tools to build fast, efficient AI, you unleash this incredible wave of creativity and experimentation. And that is how we get to the next big breakthrough.
This whole shift just opens up a world of new possibilities. We're going to see way faster prototyping of brand new ideas. More developers, not just the hardcore performance engineers, will be able to build high-performance AI. This is going to unlock new applications that were just too expensive to even think about before. Ultimately, what we're talking about is the democratization of the power to build the future of AI.
And all of this leads to one final, and I think really exciting question. As these incredibly powerful tools become as simple as writing a Python script, who is going to build the next breakthrough model? It might not be a giant tech corporation. It could be a student in their dorm room, a small research lab, or an entrepreneur tinkering in a garage. With tools this powerful and this accessible, the next big thing in AI could truly come from anywhere.